Hi, we're going to speak about the TCP/IP stack in this unit. TCP/IP stack is the family of protocols that rule the current internet. While all these protocols are also used in computer networks, TCP/IP is by far the most common of them. TCP/IP can be compared to the OSI model as a simpler and more efficient implementation of the conceptual 7-layer models of OSI. TCP/IP deals instead with 7 with 4 layers of communications. Data packets are passed top-down for transmission, as in OSI. TCP/IP doesn't specify the network access layer, so it's quite common to mix the OSI model and the TCP/IP model and talk about physical layer and data link layer instead of the network access layer. Here you can see the comparison of the two stacks. That's it. Here we can see an example of the data flow in a remote shell session login. Someone that is accessing a remote computer to control it from a shell session using TCP/IP. Each layer, as you can see here, adds headers and creates a new data structure encapsulating the one that was handled by the layer that's over it. We can see how data is encapsulated. For example, here in the second figure, we can see how the data from application layer is encapsulated in transport layer with a header, then the data from transport layer is encapsulated in internet layer with another header, and then it is encapsulated in the data link layer with another header and footer in this case. On reception, we can see it here. Each layer strips the headers added by its counterpart in the sending device, then performs the operation that are assigned to it, and then passes the resulting data to the layer over it. Look, you can see it here as it decodes it and then passes the resulting data structure to the layer over it. Data structures have different names in the different communication levels. For example, here it's called frame, let me see, here it's called datagram, here it's called segment. If the connection has to pass through several network devices, they use the same mechanism, but only up to the level in which they work. For example, a level 3 device, it's a router, it's a device that is able to connect different networks. It only goes up to internet layer, that is called network layer in the OSI model, as you can see here, and then uses the other network under it to communicate with the next device. If here we don't have any, but if the connection was made at level 2 in the OSI model, that is something that switches do, and they work inside a local network, so they only go up to OSI layer 2 to communicate with the other one. This is inside the network access layer in the TCP/IP model. The host, as you can see, hosts use all layers to communicate from one process to another process. Well, how are standards made in internet? And standards are made by IFTF, created in 1992, that uses a method that's called request for comments, RFC. That is a consensual standard setting process where the standards are created in consensus with a broad group of different entities and then are named with RFC and a 4-digit code that nowadays is in the 7,000s for the last standards. The RFC 0001 dates from April 1969. All TCP/IP protocols used in internet are defined in the public RFCs that are constantly updated. Well, we're going to speak about internet addresses now. This is something that we also saw in the first course of the ISC series. But we're going to revisit it because they are part of the TCP/IP protocol. Internet addresses are used to locate a destination computer in order to send the packets through internet. In some sense, it's like the postal address of a computer. And every device on the internet is assigned an IP address. In the late 60s, when internet started, IP addresses with 4 bytes, that is with 32 bits, as a byte has 8 bits, were used. Because the number of possible different addresses, that is 2 to the power of 32, that is 4.3 US billion, was considered a huge number that was more than enough for all the computers that were foreseen. But with the rapid growth of the internet after commercialization in the 90s, it became evident that the address space available for IPv4 was not enough to connect all the new devices in the future, and by 1998 the IETF, the Internet Engineering Task Force, formalized a successor protocol that was called IPv6, that instead of 32 bits uses 128 bits, so it allows for 2 to the power of 128, that is more than 7.9 to 10 to the power of 28 times addresses as IPv4 had. That is more than enough for now and for the future. And now we have 2 different types of IP addresses, the IPv4, that were the first ones, and the IPv6, that are the last ones. The plan was that today all the IP addresses were going to be IPv6, because they were planning something like 2012 to change, to reach the point that all the addresses would have changed. But it hasn't been like that, because IPv4 addresses have been used for more devices that they thought they could, using very intelligent mechanisms, and the adoption of the IPv6 has been slower than was thought. Nowadays, perhaps something like I think it's 15% of the IP traffic that arrives to Google servers, it's IPv6. Both protocols are not interoperable, but they have devised gateways that can communicate machines using IPv6 with machines using IPv4. And most modern operating systems, for example Linux, Windows and iOS, they are able to support both IPv6 and IPv4. Well, our IP layer, or internet layer, we find the transport layer. Transport layer is the first that is between host, is from end host to end host. In transport layer, we find 2 different protocols in TCP/IP transport layer. One is TCP for Transmission Control Protocol, that is connection oriented, and what means that it transmits data as a byte stream, providing flow control, and that it guarantees that the data transfer remains intact and that it arrives in the same order in which it was sent. And the other protocol, that is called UDP, for User Datagram Protocol, it's a connectionless protocol that transmits the packets individually and gives no guarantees at all, but it's faster and it's lightweight. So for some users it's better TCP, and for other users it's better UDP. The transport layer addresses allow users to connect to a specific application in a computer host. And they are known in TCP/IP as sockets or ports. And a socket is a combination of an IP address, the IP address of the host, with a number that identifies the specific application of service. And this is separated, as you can see in the image, by a colon. Specific port numbers are often used to identify specific services. Of the thousands of enumerated ports, there are 1024 well-known port numbers that are reserved by convention to identify specific services on a host, for example, for Telnet, for FTP, for SMTP, that is the mail, or for web protocol, that is HTTP. We don't usually see this port number because every application is programmed to use a specific port. So when we use an IP address in a web browser to access a website, it understands that the request will go to port 80 by default. But we could have, for example, two different web services in the same machine with the same IP address, and we could be using a port, for example, 8080 for the second web server. So, and we can put that in the address bar of the web browser. Well, TCP/IP protocol suite encloses far more protocols than the basic ones we have commented. You can see here in the image some protocols that use TCP, other protocols that use UDP. For example, you can see DNS, DFTP, DHCP. On the other side, you can see, for example, HTTP. And here in the image, you can see how does this fit in the OSI 7-layer models. With this, I finish.